recording here. All right, so welcome back to everybody. It's wonderful to see you all. Looks like almost every name I recognize from the previous years. So it's good to see you again. I think there are some new people who have signed up, so hopefully they'll be joining soon. But maybe there's some delays with the data distribution. Oh, okay, Harrison, fun. Okay, good. Good to see you. So now that I'm recording, so I have your record for attendance. Please, as always, type your name into the chat so that we know that you're there, because anybody who bought your data, we need a record that you came today so that Sanjay can give you a reimbursement afterward. Okay, well, I hope everybody had a really great summer. I enjoyed my summer, and I have been looking forward to getting back to our program. And this year is going to be a little bit different, but I think it's going to be something that you enjoy, and I think it's going to it's responsive to a lot of what people wrote in the feedback from last year. So basically, we're going to do calculus. I'm going to talk some more about this, but there were various people who decided they wanted to do limits, or they wanted to do derivatives, or they wanted to do functions, or they wanted to do relations, or they wanted to do sequences and series. And all of these things are together under the umbrella of calculus. So we're going to address all of those topics this year in the session. Okay, so okay, good. So let me why is it here? Okay, so I had this introducing myself, but I think everybody here has been here for a previous session, so I'm not sure if I need to really introduce myself again. I thought there might be some new people, but maybe the new people will be coming next week. So I'll do it anyway, but you guys have probably all heard this before. I'll go through it quickly. So wait, why is this? Okay, so I'll go through this just very quickly. So I've been working in Liberia now for 13 years. Started from meeting Mr. Randolph, who I met at Hunter College High School when I was a student, and he worked in the science labs there. So I've been 3 times to Liberia in summer of 2011, 2013, and 2017 to run general STEM workshops. So they were not just math workshops, but for all fields of STEM. And they were in Monrovia, at BWI, in Kakata, in Cuttington University, in San Marco, and recently in Ganta. So this year is now the 4th year of the iHelp Liberia Mathematics Training Program. So we have funding from the U.S. government, from the National Science Foundation, to run the program for 5 years. Okay, so this is the 4th year out of the 5 years that we're going to run it. And I've also organized Math Olympics contests for high school students in Liberia in summer 2013, 2017, and 2018. And in 2017, one of the participants was Clinton Quee, who's been a workshop participant over the last few years. And he recently announced on the chat room that he's starting a master's program in South Africa at Ames in mathematics. So we wish him all the best. It should be a very interesting year for him. And then in the last year, there's also been high school students who've participated in the WITS mathematics competition, which is also run based in South Africa, but it's open to participants from all over Africa. And we'll run that again this year, and hopefully that the students will participate there. That will outlast the 5 years that this program runs. So that hopefully can be a perpetual participation for everybody. Okay, so welcome. We have a couple. Okay, somebody new. All right, Anthony Lumba, welcome. I think you are a new participant. It's good to see you. So for everybody who just came in, please type your name into the chat so that we can reimburse you for your data. In general, we will get you your data before the class starts. This week was an exception because all the administrators were hard to reach in rural areas, but usually you'll receive your data before class. Just for today, you had to purchase your own data, but you'll get reimbursed promptly. I already sent the funding over to Sanjay, so the data reimbursement should go quite promptly. Let me mention also, for the people from before, I know you have still not received your certificates for last year. I have them. They are done. I have to get them to Liberia, and I have to also know who is going to be signing it from the ministry. And I think the reason for the delay is that there is a new administration in Liberia, and so the person from the ministry from before is not the same person as the ministry now. And we have to work out, with the new ministry exactly who's going to be signing it. But the certificates are prepared, and they will be, sent over as soon as Mr. Randolph has somebody going to Liberia, which should be soon, and as soon as we know who's going to sign them. So I will keep you up to date on the procedure for the certificates, but rest assured, we have not forgotten about you. If you participated last year, you do have a certificate, and it will be coming. Okay. I'm apologize very much for how much of a delay there's been. We usually like to get you the certificates during the summer, and unfortunately, it will probably happen in the fall instead of in the summer. Okay, but for all of the people who participated last year, your certificate is coming, so don't worry. Okay, great. So a little bit more about me. Again, most of you know this, but there are one or two new participants. So I received my bachelor's degree in mathematics from Harvard in 2003, and then I did my PhD in pure mathematics from the University of Pennsylvania in 2009. So I studied number theory, I studied prime numbers and their relation to geometry in my PhD. And I'm currently an associate professor of mathematics at Baruch College, which is one of the colleges in the City University of New York system. There's 11 colleges through New York in the City University. And so I teach courses in undergraduate math and graduate level math, and I do research in number theory and algebraic geometry. And before coming to Baruch, I taught at Columbia University, also in New York City, and at the University of Virginia in Charlottesville, Virginia. And I will probably be teaching at Baruch for a long time from now on. So I want to talk a little bit about what we're going to do this semester. So based on popular demand and based on the feedback and also based on something that I've wanted to do for a while, our focus this semester is going to be calculus. Okay, and not just calculus, and we're not going to jump right into calculus. You can't just jump right into calculus. So we're also going to study the preliminary material that led up to calculus. And I think the majority, more than half of the people who responded to the survey from last year requested some of this material, either the calculus material or the material that's leading up to calculus. So overall, this material will be a little bit more advanced than what we've studied in the past 2 years. We've done statistics, we've done trigonometry, we've done modular arithmetic, we've done probability, we've done exponentials and logarithms, and we've done some vectors and matrices. So overall, this material is on average a little bit more advanced than all that. But I think everybody's ready, especially if you've been participating in the program for the last few years, which most of you have. And we will cover the material that we need to cover in order to make you prepared for calculus. So it is, among the most important material that your students will learn, even the preparatory material in that case. So let me take a break now to go over the syllabus. I sent this syllabus out over the chat room about 30 minutes ago, so it's the same syllabus that you have, but let me go back over it. Hold on, this is too small. Let me do that. This should be better. Okay, so this is me, Andrew Obis at CUNY Baruch College, New York City. So one of the other pieces of feedback that I got was that people wanted more time, that it was too short. So unfortunately, I'm only available on Fridays for teaching, but we are extending the session. Okay, so for now on Fridays, we're going to run from 4 o'clock to 6 o'clock instead of from 4:30 to 6:30. So we're going to, or 4:30 to 6:45. Okay, so we're going to have an extra hour every Friday. There are a couple of days that we have to miss this semester, but hopefully the extra time will help make up for that. Okay, so the Zoom link for the course is here. It's oh, sorry. Okay, yes. Let me try to do this. Let's see if I can do it like this. Better? Okay. Okay, hopefully that's better. So the Zoom link is the same as it's always been since the beginning of the course. It's at this link, and the password is the same as it's always been. And there is a website and a YouTube channel. I know I tried to start that last year, but Baruch actually, my college had a big computer attack last year, a big cyber attack, computer virus, and the websites were all down for a while, and then they ended up having to change up all of the websites. So there's a new website. It's a different address than what it was for last year. So here's the address. You can link to it from the what I sent you in the chat if you want. And I'm going to post all the lecture notes and all of the course materials there. And I'm also going to post links to the YouTube channel. And on the YouTube channel, that's the same as it's always been. The YouTube channel is where I'm going to post recordings of all of our sessions. Okay, so the old sessions are all there from the previous classes, and I'll post more of them. And that YouTube address has not changed; it's the same as for all of the previous years. Everybody who's here knows the chat room. You're all in the WhatsApp chat room. I assume if you're not, then contact Sanjay and she'll add you, but I assume that everybody's there. This is going to be the main way I get information to you, or that Sanjay or Charles or Abraham get information to you about the course. So we'll be posting important notices to this chat room from time to time. One more reminder, by the way, if you haven't typed in your name to the chat, please do it. I need your record for attendance. Okay, so in particular, I think Anthony has not, you haven't typed in your name, and I don't know if George has typed in your name. I remember you now, but I need to remember after the session is over. So please type your name so I have the record that you attended. Okay, so we will have a textbook. I'm going to send a PDF of the textbook over the chat for this time. So the textbook is called Single Variable Essential Calculus, second edition by James Stewart. James has written a lot of calculus books, and this is the one that that fits the best for what we're doing this semester. Okay, so I haven't sent that yet over the chat room, but I'm going to send you a PDF of the textbook over the chat room so you can refer to it. Okay, so the theme that I mentioned already is going to be calculus, specifically differential calculus. And so a lot of the things that we've done in the past years are maybe material you've seen, but you don't know so well and you need a review of. With calculus, and maybe some of you have seen it, but maybe some of you haven't. So this could be completely new to some people in the room, and that's fine. We're going to go at a pace that hopefully allows it to make sense and be comprehensible, even if it's new. Okay, so we're going to be studying what's called differential calculus in the fall, and we're not going to finish it in the fall, so we're going to continue it in the spring, and depending on what people want to do afterward, we can study some integral calculus, and we can focus more on sequences and series, if this is what people want to do. But in order to build a foundation to study calculus, we need to spend some time at the beginning of the term learning about relations and functions and limits. And I know these are all part of the math curriculum in Liberia that Sanjay sent to me. So this material on relations and functions and limits should be helpful to everybody who's teaching in the secondary school curriculum. Okay, so like always, there's going to be practice exercises. I think for this year, the practice exercises are maybe even more important than they've been in previous years because calculus is so cumulative. So very important to try the exercises. We'll spend time going over them. Now with the 2 hours, it'll be good to have lots of extra time to go over this. And then the attendance policy, I would say it hasn't changed, but it's perhaps even more important than it's been in previous years because these sessions really do build on each other. So this probably doesn't apply to anyone who's here now, but this course will be very difficult to join once it's gotten going. So if somebody hears about this in December or in January and wants to join, they're really not going to be able to because it's too cumulative. So you have to be with this from the beginning, at least joining in the first 2 or 3 weeks. After that, it's going to be too hard to join. And And if people hear about the program in January or February and they want to join, then they're going to have to wait until next fall. So I'm not going to give data funding in the spring to anybody who hasn't been consistently attending in the fall. Okay, because it's too cumulative to join in the spring. It's nothing's going to make any sense. It's not going to be worth it. Okay. And so, yeah, so this is what I said. So the material will be cumulative for the whole year. So only if you attend consistently in fall will you get funding for data in the spring. Okay. And if you're not able to attend in fall, that's fine. We are running the program for 5 years. So there will be a 5th year next year. And whatever topic we do next year, that's not decided yet, but it will be something that anybody can join. It's not going to require that you came this year. Okay. So there can be new people who join there. Okay, and so now we also just have the schedule of topics over here. So this is going to be today, just doing some introductions and talking about what calculus is, what we're going to study. And then what we see is the first half of the term is mostly prerequisites for calculus. So we're going to talk about relations and functions. We're going to review the standard functions, trigonometric functions, logarithms, exponentials, polynomials, rational functions, these everything that we need to know. We're going to talk about limits of functions in the finite case, limits of functions in the infinite case, and continuity. These are all kind of important basic concepts for being able to discuss calculus. And then we'll get into differential calculus. So differential calculus involves something called a derivative. So we're going to talk about the meaning, what a derivative is, and we're going to talk about computing simple derivatives. And then we're going to talk about how this applies to physics at the most basic level, how this helps us describe motion in physics. We'll do a little bit more about computation of derivatives, and then we'll do the other. These are somehow the 2 most fundamental applications of calculus. One is to use it to describe motions in physics, and the other one is to use it to describe what's called optimization. You have some system, you have some variables that you can control, and you want to get the best results. Maybe you want to make the most profit in your business, or you want to build a fence that encloses the greatest area, or anything else. There's various things that you might want to maximize or minimize, and calculus is kind of the fundamental tool that people have developed that helps you do this. Okay, so these sessions are going to have the most major applications of calculus, and then when we continue in the spring, we're going to do more applications of differential calculus, and then decide whether we want to move on from there to integral calculus, or if we want to move on from there to talk about sequences and series. Okay, so this is the syllabus for the class. And we have September 13th. That's the first class today. And there are unfortunately a few holidays where we're not going to be able to have class, but hopefully with the 2-hour time session, we'll get enough time to cover all the material. Okay, so before we move on, are there any questions about the syllabus?
Yes, I have a question.
Yes, Miata.
I was thinking, is it possible that we do a little of what we call data analysis? Because in our everyday work, we found out that we do little data,
Mm-hmm. So
So I was thinking,
yeah, so data
if we could
analysis,
add.
yeah. So we did a little bit of this last year when we did our statistics unit. We can try to do, so probably this semester we're probably not going to do that. That's not going to fit into the topics of the course for this semester, but we can certainly try to do some either in the spring, or if you want it for the last year of the program, then we can do it in the last year if we want to do some data science and some more advanced statistics. And we did kind of basic data analysis when we did statistics last fall. But if we want to be doing more advanced data analysis, trying to talk about correlation and covariance and inferential statistics and things like this, yeah, if there's enough demand for that, we could definitely do that in another term. I think probably not during this term. It
Okay,
won't really
thank
fit
you.
into the material. Okay, you're welcome. Other questions? Okay, great. All right, good. Welcome, everybody. For the people who have just joined, maybe actually there's a couple of new people who have joined the group. So maybe you can quickly introduce yourself, who you are and where you teach. So it looks like Nike-san, I think, is new. Do you want to introduce yourself, Nike? It looks like you're off. Or how about, oh, there you are. Yeah, Nike? No. Or how about Anthony Lombe? Would you like to introduce yourself? Yes. Hi. Hey, Prince. Oh, Nike, there you are. Yeah, hold on. Sorry, I'm just gonna mute everybody, and then I just want some new people to introduce themselves. So, Nike, can you introduce yourself? Sorry, you're muted. We can't hear you.
Yeah. Hello.
Hello.
Yeah. I'm saying my name is
Sorry, not getting you very clear, unfortunately.
Wow.
Sorry, I'm not getting you so clearly. Maybe we can come back to you, because I'm not getting you clear. Okay. How about, okay, well, welcome in any case. Hopefully the connection will get better. Anthony Lombe, do you want to introduce yourself?
Hello.
Hello. And say maybe what school you teach at, where you're from, how you heard about the program. Hello.
Anthony Lombe.
Mm-hmm.
Just Michael Catholic School.
Mm-hmm.
I learned about the program from the Brewer instructor.
Mm-hmm. Great. Well, welcome to the group. Who else is new? It looks like Enoch Dwe Jr. Enoch, would you like to introduce yourself?
Yeah, I'm Enoch where and I joined from Monterrey County.
Mm-hmm.
Hello, good evening.
Great. Okay, welcome.
Yeah.
And Hassan Rogers. Let me just mute everybody first. Then I think Hassan Rogers is new. Would you like to introduce yourself to the group?
Yes. Hi.
Yep. Hi.
Are you hearing me?
Yep. Getting you good. Getting you clear.
Yeah, I'm Hassan Rogers from Calcutta Road Teacher Training Institute.
Mm-hmm.
I teach natural science at the B certificate program.
Okay. Great. All right. So welcome everybody. And then I think everybody else. So Harrison Fawn, Armstrong Zarwalo, Christian Myers, G. Francis Tonzia, George Larbe Indy, James Caselli, James Va, Joyce Sioe, Kaifala Talawale, Miata Tarpe, Deborah Strother, Prince Nenya, Uriah Innes, William Boandolo, all of you I know. So it's good to see you all again. Yes, I'm looking forward to the rest of this term. Okay, it seems like enough people are in. One more time, if you have not yet typed your name in the chat room, please do so, just so, because if I don't have your record for attendance, then we can't reimburse your data. Okay, so I want to make sure that you get it back. Okay, great. Okay, and throughout this time, if you want to interrupt, if you have a question, you can always turn on your microphone, ask me a question, or if you want to type a question into the chat, I read it and you'll be able to get to me. The one thing I ask is that when you're not speaking or asking a question, to please have your microphone on mute so that the background noise doesn't disturb the other participants. Okay, so the training has a website. This is what I said already in on the syllabus. The website is not updated yet. So this has, it still has some of the stuff from last year and it doesn't have everything from last year. So I will update the website next week so that it will start to have links from the recordings for this year. And it will also have the lecture notes that we have. And I'll send out a PDF of the textbook on the chat room. Okay. So I also always post the lecture notes and the video recordings right after class. I always post them on the WhatsApp chat room. So if you don't go to the website, you can always still link them on the chat room. The web address is kind of long. It's kind of hard to remember. So if you can't remember it, instead just Google Andrew Obis Baruch. That will get you my main website. You click on my main website. Then if you scroll down to the bottom, there's a link to the Liberia program website at the bottom of the page. So that's probably a little bit easier to remember if you want to find the website for the program. And then starting next week, we're going to give out homework after every meeting, and we'll discuss that. And so there won't be any homework today, but starting next week, we're going to give that out. And usually we'll discuss the homework at the beginning of the class. Okay, so what is calculus? So we're going to be studying calculus this semester. So what is calculus? Well, calculus is the mathematics of motion and change. Okay, so if a lot of mathematics is about, static things, trying to measure something static, trying to, understand, trigonometry is about understanding triangles, and maybe analytic geometry is understanding properties of graphs of equation. Calculus is about things that are moving and things that are changing. Okay, and it's not only about that. There's several different things that are all, grouped together in what's called calculus. So furthermore, in calculus is what we use to extrapolate facts we know about straight objects to the case of curved objects. So for instance, you know how to calculate the area of a rectangle. It's base times height. But if I give you a curved shape, then how do you calculate that area? That's much less straightforward. That's a problem that calculus helps you solve. Okay. And then lastly, I should say that calculus is about infinite things. And so sometimes this means infinitely big things. We want to know like what functions do or what graphs do when you go out to infinity. But maybe more importantly, it's about infinitely small things. Okay, so a lot of what we talk about calculus will be about what are called infinitesimals, which means I think actually I may have spelled this wrong. I think there's only one S. So infinitesimals about what happens when you look at infinitely small things. And this is one of the difficulties that people have with calculus is that we're not used to thinking about infinitely small things. Okay, and so thinking about that requires a different mindset, a different way of thinking, and that's something that studying calculus will try to make you better at. So traditionally, calculus has two different facets. So there's something called differential calculus, and then there's something called the integral calculus. Okay. We'll be doing the differential calculus this semester, but we'll talk about the integral calculus for a little bit probably in the spring. Okay, and I'll just say that many people consider calculus one of the most brilliant creations of the human mind, and calculus has been around for about 400 years now, and it's completely revolutionized physics. Lots and lots of modern technology would be completely impossible based on calculus. Anything involving without calculus, so anything involving modern electronics, GPS, satellites, spaceflight, lots of current engineering techniques. These all rely fundamentally on calculus. So it has lots and lots and lots of applications, and we'll talk a little bit about what those applications are, later on today. Okay, so let's first talk about a little bit about what differential calculus is. So let me give you a problem, which I'm going to call the odometer problem. So suppose a car is driving in a straight line, and we sit inside the car and we watch the odometer. So we watch, how the miles or how the kilometers increase while the car drives. And so the question is, can we determine what speed the car is going at a given time? Okay, so when I say that we sit in a straight line and watch the odometer, let's imagine we also have like a watch or some sort of timing device. Well, what happens? Well, if we watch the odometer, we can make a graph. We can make a graph on 2 axes. And so in the x-axis, I'm actually going to label it as t. T is going to be the amount of time that's elapsed. And on the y-axis, I'm going to label it d for distance. Okay, so here we have a time axis and we have a distance axis. And if you're watching the odometer of the car and you can time it well, then you can draw a graph based on, so the distance, this could be also just the odometer reading. Okay, so how many miles are on the odometer? And if you're watching carefully and timing carefully, then you can make a graph at each given time. Maybe we'll call time 0 as the beginning of the ride. Okay, so at time 0, you haven't gone any distance, and as time goes on, you've gone some more distance. And if you're timing carefully, then you can draw the graph of time versus distance. Okay, and so the question is, from that graph, do we know what speed the car is going? Okay, so first, let's imagine the car is going at constant speed. Okay, so the speed of the car remains the same throughout the ride. So what happens when the speed of the car remains the same? What do we know about constant speed? Constant speed, we know that in this case, distance is equal to speed times time. Right? That's how you calculate distance. It's equal to the speed times the time if the speed is constant. And what that means is that as time goes on, the distance is proportional to the time, right? So another way of saying this is that distance is proportional to time. Okay. And so what that means is if we draw this graph, it's going to be a straight line. As time increases, distance is going to increase at all. Distance is going to increase the same as with time. It's going to be a straight line, okay, if the car goes at a constant speed, right? Because if the car is going, say, at 20 miles per hour, then every hour, the car goes an extra 20 miles. In the first hour, it goes 20 miles, and the next hour, it goes 20 miles, and so on, okay? So if a car goes at a constant speed, then the graph of time versus distance is going to be a straight line. Okay, graph is going to be a straight line. Okay, the car goes at a constant speed, the graph is going to be a straight line. And so how do we figure out what the speed is? So if I give you this straight line that determines the distance based on the time, then what aspect, what attribute of this line determines the speed? Does anybody know the magic word here?
Yeah, repeat the question
Yes.
again.
So I want to know if I showed you this graph, like let's say, let me even give a marking. So I have a straight line. Let's say that my time is, over here, this is two hours, right? So let's say this time is in hours. Okay, and then this speed over here, sorry, so the y-axis is distance. And so let's say that I mark 40. This is measured in miles. So this is my point over here. Let's say the graph goes through the point where I have 2 for hours and 40 for miles over here. So from this, can I calculate the speed that I'm driving at?
Yes.
Yes.
Yes. How do I do it? George?
Yes. Yeah, you can.
Yeah, so what do you do?
Because speed will be equal to distance divided by time.
Right. Right, so speed is distance divided by time.
Yeah.
So in this case, that's going to be 40 miles divided by 2 hours, and that's going to be equal to 20
20 miles per hour.
miles per hour, right?
Yeah.
Okay,
Yeah.
good. Thank you, George. Okay, so this is how to do it with these numbers. But in general, if I just give you a line, so what is this 20? How can we see this 20 in the graph? Well, 20 here is the slope of this line, right? The slope of this line, remember what the slope of a line is. The slope is how much it rises divided by how much it runs. So in this case, the speed is the distance. This is how much the line rises. This is the distance divided by the time. This is how much the line runs to the side. And that ratio is called the slope of the line. Okay, so in this numerical example, the speed is 20 miles an hour. But in general, if you're going at a constant speed, this graph is going to be a line. And so we get that the speed here is equal to the slope of the graph. Okay. So if a car is driving at a constant speed, you can graph how much distance it goes versus how much time. That graph is going to be a straight line. And if you look for the speed of the car, that's going to be the slope of that line. Okay. So this is how slope determines this is how slope determines speed. So kind of the answer to this question is that if the car is going at a constant speed, we can do it, right? If the car is going at a constant speed, even if we can't look at the speedometer, let's imagine the speedometer is broken. I can't look at the speedometer, but I can look at the odometer. So I know how many miles it's going. I can keep track of the miles versus the time. I can draw that, and I can take the slope of that line, and I will be able to get the speed from that. So I can calculate the speed even without looking at the speedometer. Okay. Is that okay? Any questions on this?
Yes, I have a question.
Yes.
What if the car is not going at constant
What is
speed? What if the car is not going at constant speed?
That's a great question. Right. That's the next slide, right? So right now, this is a standard problem, right? We didn't use any calculus to do this. This is just a proportion. Speed was distance divided by time. There's no calculus at all, right? So now Hassan asks, what happens if the car is not going at constant speed? And that's exactly where we're going to need to use calculus. So I'm going to answer that. So before I go to that, any questions about this constant speed case? Okay. So yeah. So in reality, cars don't go at constant speeds. So what happens if the car speeds up or slows down? So I'm going to draw the same graph. Or I'm going to draw the same axes. So this is t for time in hours. And this is going to be d. This is going to be distance in miles. And you know that if a car starts a journey, then it doesn't immediately go at constant speed. Even if eventually it's going to go at constant speed, it still needs to accelerate from being stopped. When a car starts, it's going at 0 miles an hour. It's not moving, and it has to accelerate up to a given speed. So what might happen is that the car starts off moving slower, and as it accelerates, it moves a little bit faster, and then maybe it gets to its destination and it slows down there also. So the actual graph might look something like this. So it starts off going slower, then it starts moving faster. Moving faster means that the graph of the curve gets steeper, right? Because you're covering more distance in the same amount of time. And then as it's getting closer to where it's going, maybe it levels off a little bit and then starts going back down again until it finally, the speed, oh no, sorry. Let me erase that. So it starts getting faster, and then maybe it starts getting slower and slower. The distance always increases because it's going in a straight line, and then maybe it stops over here. Okay. So now imagine here, I have 2 hours. Let's say again, I'm going 40 miles, and it still takes 2 hours, but now this is not a straight line. So I can say here, you know, on average, the car goes 40 miles in 2 hours. So the speed is 20 miles an hour. Okay, so that's true on average. That's true if I draw a line from where I start to where I finish, and I look at the slope of this line. I'll just draw it as a dotted line. I have a line like this from the beginning to the end, and I look at the slope of that line. That slope is 20 miles an hour. Here, this is the slope of the red dotted line. Right? But what if I want to know, for instance, what is my speed at, let's say, 90 minutes? So let's say here, I don't know, here, let's say this is, 1.5 hours. Okay. And now I want to know, so the question is at 1.5 hours, what is the speed of the car? Okay, so if you were riding in that car and 1.5 hours into the trip, you looked at the speedometer, what would it say? What's the speed right there? And this is now a problem that you need calculus in order to do. So we've already seen that speed corresponds to slope here because it's distance divided by time. And if we're going from one point to another point, we can calculate the average speed by taking the slope of the line that connects those 2 points. But if we're looking at what's going to happen at one particular point, what you actually have to do is take the slope of the tangent line to the graph at that point. So this here is what's called the tangent line. It's the line that hits the graph only at that one point, and it hits it smoothly there. So if you want to know at 1.5 hours, what's the speed of the car? The answer here is that it's the slope of the, and I'll write this in green, it's the slope of the tangent line. Okay. So, and what you see is that this slope starts out as 0, right? You start off going horizontal. This tangent line is going to be horizontal. As the curve ramps up, the slope gets steeper and steeper and steeper. So over here, maybe the car's going the fastest because that's the steepest part of the graph. So at that point, the car's probably going to be driving faster than 20 miles an hour. And then the car starts to slow down again as it's getting close to its destination. And maybe after 1.5 hours, I don't know exactly what the slope of this line is, but looking at the graph, it looks like it's probably a little bit less than 20 miles an hour, right? Over here, this line seems like it's not increasing as fast as the red line, right? See, these lines aren't parallel, right? The green line and the red line look like they'll eventually meet. So that means that the green line is less steep than the red line. So maybe over here, it's only going 15 miles an hour. Again, I haven't given you a specific equation. There's no way that you can actually calculate the number, but I want to just get a qualitative sense that here the car starts off slow, then it gets faster, and then it slows down again. And if we want to know how fast it's going at any one point, in fact, you have to take the slope of the tangent line is what's going to tell you that. Okay, so we'll talk about this more when we talk about derivatives, but one of the main problems that differential calculus tries to solve is if you have a graph, how can you figure out the slope of the tangent line? And in practical terms, you can say, okay, if you know how your distance is related to your time. So if you know how your odometer is measuring how far you've gone based on time, then you can use that to figure out your speed at any given point, okay? Speed in general is a slope, and at constant speed, it's always the same slope, but when speed is non-constant, it can vary, and each point has its own tangent line, and the slope of that line will differ depending on which point you're at, okay? And one of the main things that differential calculus does is it helps you explain, or it helps you figure out what that is, okay? So we're going to do this in much more detail later on with equations and numbers and everything. But for now, I just want to give the basic concept, which is that if you have a graph of distance versus time, slope corresponds to speed. And if you want to know speed at one point on a curved graph, then what is the slope? Well, you have to take what's called the slope of the tangent line. Okay. Any questions on this?
Yeah, hello, sir.
Yes, Prince?
Yeah, thank you so much for this information. Even though I came late, but I never knew today. Up to the question, we didn't have any number given to the question, but then how did you get to 40 in $2 meters divided to find the speed? How?
Sorry, so I'm not getting you that clear. So I'm just saying this is just part of the problem. So imagine that the car takes 2 hours to drive to the destination, and the destination is 40 miles away. So we're just that's just a given for the problem. So destination's 40 miles away, and it takes 2 hours. So if you want to calculate the average speed, you just take the total distance divided by the total time. Okay, just like we did over here, right? The speed is just the distance over the time. Your average speed over a journey is the total distance divided by the total time. So in this case, if the car takes 2 hours to drive 40 miles, then the average speed is 20 miles an hour. Okay. And in this case, it's the same thing. The car still takes 2 hours to drive 40 miles, but it's not driving anymore at a constant rate of 20 miles an hour. It's driving at an average rate of 20 miles an hour, but it's actually starting off slower and then getting faster and then getting slower again, right? You notice because right here, time is running, but the speed isn't actually increasing. The distance isn't increasing that much. And then the distance starts to increase really fast, and then the distance starts to increase slowly again, okay? So what is the speed at any given point? It varies, even though on average it's 20 miles an hour.
Okay, thank you. So that means anytime the question is given, you will be having its number, right? Which is
yeah. If you have an actual question, I have to give you some more numbers. Right now, you can't actually figure out the slope of this tangent line because I haven't told you the equation of the graph, right? Okay, I'm just trying to get a kind of qualitative to look at it and see, we see in one place the tangent line is a little flatter, and over here the tangent line would be much steeper, for instance.
Okay, thank you so much, sir.
Okay, you're welcome. Other questions?
Hello.
Hello, yes. Who's question?
Yeah.
Enoch.
Yeah. What if you were given a tangent line and to find slope, and for me actually decided to use the first principle of derivative by using the limit of the function.
Yeah, I mean, this is how you have to do it. Yeah, this is what we're going to go over when we.
Yeah, because for this one, if you are given the slope of a tangent line, will be you have to use the limit of f for h minus f for s or h. So why you have to actually obtain the first derivative of the function.
Yeah, exactly. I mean, you're exactly right. So we're going to go over doing that. Yeah, I haven't told you how to find the slope of the tangent line. The answer is what you're saying. But just for the beginning, that why do we even care about the slope of the tangent line? So one thing is that the tangent line tells us this speed if we have a distance versus versus time graph.
Yeah. Hello.
Yes. Hello. Yeah.
Yeah. I'm so sorry. My network like flaunting, but I have a series of questions to ask.
Sure.
Yeah. So, what if the car starts at some point on at some distance, for example, 5, and continue in a
So if the car
Hello?
starts over here at 5.
Okay, yeah.
Yeah.
For example, it start at 5 and continue in a straight path in respect to the time. Yeah.
Right. So it doesn't really matter where it starts, right? Because all that we care about is the slope of the graph, right? So no matter where it starts, that slope is always going to be the slope of the tangent line. So I started at 0 just because I wanted to call it distance 0 because it's easier. But I could start at 5 also. We could say, you know, if you're going to use mile markers on a road, then wherever you start, you could mark it at that mile, and then you're going straight. And so you're starting not from 0, but from somewhere else. I mean, that's fine. It doesn't change the problem very much.
Okay. Yeah. I understand.
Okay. I see a question from Armstrong. So why were we using 1.5 to find the speed? It's just a question. I just said, what is the speed after 1.5 hours? I could also ask, you know, what is the speed after, I could say, what's the speed after 1 hour, for instance? I could put that over here. If I wanted to know what's the speed at 1 hour, then that's fine. I'll just have a different tangent line. Maybe I'll draw it in purple. So in that case, the car's going much faster at 1 hour than it's going at 1.5 hours, right? So maybe the tangent line looks like this. This slope here is the speed at 1 hour. Hey, this is if we looked at 1 hour and looked at the speedometer, then that would be the speed. 1.5 was just an example point. But the point is, you can do this at any point, at any time. You can look at the slope of this tangent line, and that's going to tell you how fast the car is going at that time. Okay. Does that answer the question? Other questions? Okay. Okay, so let's move on. So this is the basic problem that calculus is invented to solve. And it, of course, it has many more applications than just finding a speed. We'll talk about those a little bit. But let me talk about the other problem, which is kind of the beginning of integral calculus. So, you know, I called this the odometer problem, which is if you can only see the odometer, can you figure out the speed? So now I'm going to ask the opposite problem. So let's say this is called the speedometer problem. So suppose a car is driving in a straight line and we sit inside, and now we can watch the speedometer. So we see exactly how fast it's going at every point. Okay? So the question is, can we determine how far the car has gone? So imagine the odometer is broken. You can only watch the speedometer, and you want to determine how far the car has gone. And so again, if the car travels at a constant speed, this is not that hard to do. So what I'm going to do is draw another graph. But it's also going to be the graph of what I can observe. So this horizontal axis is still going to be t. It's going to be the time in hours. But here, this axis is going to be, I'm going to call it maybe v for velocity. So this is going to be speed in miles per hour. Okay, so what happens if the car goes at a constant speed? So let's say I'm driving 20 miles an hour the entire time, right? So if I'm driving 20 miles an hour the entire time, then the speed versus time graph looks like this. It just looks like a straight line, right? So let's say that I drive for 2 hours at 20 miles an hour. Okay, so this would be the constant speed, 20 miles an hour. So example, 20 miles an hour. Okay, so question is, if we know the speed and we know the amount of time, can we figure out the total distance, right? So, and again, we can certainly do this, right? Because distance here is equal to speed times time, right? So if the speed is 20 miles an hour and the time is 2 hours, these axes are not on the same scale, that's fine because they're measuring different things, then the total distance traveled is Well, we know in this case, we know what it is, right? It's going to be 20 miles an hour times 2 hours is going to be equal to 40 miles. Right? Right, it's going to be 40, right? And so the way we figure this out, how can we see this geometrically? What is 40 miles here? Well, 40 miles here is the area of this rectangle, right? Okay, so here 40 miles is the area of this rectangle. So 40 miles, this corresponds to the area of the rectangle. Right? So if I draw a graph of my speed going at 20 miles an hour, and I go for a certain amount of time, then the total area of this rectangle under the graph is exactly the distance traveled, right? Because over here, this is my time, and then over here, this is my speed. And so I multiply them together to get speed times time, which is distance. And geometrically, what does multiplying these two things together mean? It means finding the area of the rectangle. Okay. Okay, so if a car goes at a constant speed, I can easily figure out the distance traveled by just multiplying the speed by the time. And geometrically, what that looks like is I just draw a graph of the speed, and I then calculate the full area under that graph. Okay, so for a constant speed, this is not hard at all. Okay. All right, any questions here? Sure. Okay, so this is basic, and this in particular is not calculus, right? This is distance equals speed times time. This is something that we know, and we're not using any calculus in order to do this, right? Because generally when we're looking at static things that don't change, things that involve straight lines, then we don't need any calculus to do that, okay? All right, so now let's do the same question, but now the car's speed is allowed to vary, okay? So what if the car speeds up and slows down? So same problem, we're watching the speedometer and we want to know how far the car has traveled. So I'm going to draw a graph again. Okay, so this is time. This axis is time, and this axis is speed in miles per hour. And now let's say that my speed varies. Let's say, again, I start at speed 0 because I'm starting the car, and then I speed up, and then I drive for a while at a speed, and maybe I slow down because there's some traffic, and then I go back up, and then I get to my destination, so I slow down and my speed goes down to 0, right? This is a completely reasonable way that my car's speed might look. I start slow, I then go up faster, and then I slow down because there's a little traffic, and then I go up faster, and then I get where I'm going, so I slow down and I stop. Okay, right? Speed over here, right, is 0. Okay? So the question is, how much distance have I traveled? Well, just like in the previous case where the distance was the area under my speed graph, well, here, what do I have? Let me just give some numbers to make this a little more concrete. So let's say this is, the whole trip took 2 hours, okay? And maybe the top speed that I got over here was, 30 miles an hour. Maybe 30 miles an hour represents the fastest that I was ever going on the trip. But I spent a lot of the trip going less than 30 miles an hour, right? If I was going 30 miles an hour the whole time and the trip took 2 hours, I would go 60 miles. But if I'm now going always less than 30 miles an hour, sometimes getting up there, but then slowing down and slowing down again, then I will not have traveled a full 60 miles. It's going to be something less than that. And in fact, maybe you have this intuition, the total distance traveled, just like what we had before, is going to correspond to the area under this graph. Okay, so in this case, the red area represents the total distance traveled. Okay. So the red area in this case represents the total distance traveled, and it kind of makes sense, right? If you spend more time going at a high speed, then you've got more area over there. When your speed is very low, then you're not accumulating a lot of area under this curve. And that's because you're not covering a lot of distance when your speed is low. So most of the distance here is when the speed is high, and as it gets lower, you're covering less and less. Okay. So this is so this red area represents the total distance traveled in this case. And unlike in the previous case, I mean, it's the same thing. The area is the total distance that you travel. But here, this area was very easy to compute because it's just a rectangle. We do 20 times 2. Whereas over here, this is not easy to compute, okay? Because this is just the area under this curve. And this curve is some irregularly shaped thing, and it's not easy to know what it is. We might look at it and see, well, if I did the whole thing, if I was going 30 miles an hour the whole time, I know that would give me 60 miles an hour. So what we've done, we can look at it and estimate. Don't worry, I'm recording already to my computer, and I'm gonna send out the recording afterward. This is how I do it, because if I record to the cloud, it disappears in 4 months. So that's why I'm recording to my computer. I'll send it out, and I'm gonna put it on YouTube afterward. So the red area represents this total distance traveled, and it looks like whatever this area is, it's less than 60. Just from looking at it, maybe this looks like about 3/4 of the area of the rectangle. So maybe we can guess that the total distance is about maybe 3/4 times 60 miles. So, which is 45 miles. Okay, so maybe we can guess that, but of course this 3/4 here is just a guess. And it's just from me looking at this shape and thinking that it's about 3/4 of the area of the rectangle. It's about 75%. In order to actually get the answer, I would need to give you some equations, and you would need to use calculus. And this is one of the questions of what's called the integral calculus, is to try to figure out the area of these kinds of weird shapes. Okay, and it turns out, just like the differential calculus, it has many, many more applications beyond just figuring out areas. Okay, so the integral calculus is used for a lot of things. We're not really going to talk about it this semester, but given an introduction to calculus, I want to just mention that these are kind of two of the fundamental problems. So what is this problem saying? Again, if you can see the speedometer, can you figure out the odometer? So if you know how fast you're going, can you figure out the distance? That's a problem for what's called integral calculus. And the earlier one was, if you can see your speed, if you can see your distance, can you figure out your speed? That's what's called the differential calculus. Okay, and both of these questions are relatively easy if things are constant and don't change, and they're hard if things change a lot, because you're then dealing with curved shapes. And this is what calculus is developed to do. It's developed to let you work with curved shapes the same way that you work with straight shapes. Okay, any questions on this?
Muted. Hello? Hello?
Yes, question.
Yeah. I have a question.
Yes,
Yeah, what if you have another graph that behaves different way? Like, for instance, the car starts at some point 30.
So it starts off
and
going 30 miles an hour right away.
yeah, for instance, the car starts at some point 30, and due to the traffic, it go down in behavior, and sometimes go up and go down, go up and behave somehow, so and reach to some point at 3.
At t equals 3?
Yeah, t equals 3.
Yeah, so I mean, I can draw this. So if we just had a different graph, we looked, here's 30, here's t equals 3, and maybe the graph looks like this or something.
Yeah, show something, I mean.
Okay. Yeah, well then what you have is, you just, again, have the area underneath. right? So in this case, this is the area that you're trying to find.
Okay, but in so doing, can I use integral calculator to find the area under the curve? Can
Yes.
I do so? Yeah.
Yes.
Okay.
Yes, you can.
Okay.
And again, of course, we haven't done integral calculus, but here it looks like 30 is maybe about the average speed, right? It goes faster for a while, and then it goes slower for a while, and then faster, and then slower. So maybe a good guess here is that you do cover about 90 miles, about exactly 30 times 3. Because
yes.
this looks like almost the same area as if I just drew a straight line instead, because there's some extra stuff on top, but it's missing stuff underneath. Yeah.
Hello.
Yes. Hello.
Yeah. So if you draw a straight line starting at 30 to some point 3,
yeah.
Then okay, there just like that. If you draw a straight line, what can you say about the point I left up? The one I left all I went up due to the traffic that you went zigzag.
Mm-hmm. Yeah, so the way I drew this, it looks like the area. So I'm going to draw the green area as just the total area under the straight line. Sorry, this is a little bit harder to draw. Let me just do it on. This is the green area. It's just the box, just a rectangle, right? Yeah. So the green, it looks here just from the way I drew it that the green area is roughly equal to the red area. Right? Because it looks like the green area basically has this, the green area has this extra piece. This part here is green and not red. And the red area up here has 2 parts that are red and not green.
Yeah.
And from the way I drew it, it looks reasonable that the combined area of these red parts is about equal to the area of this green part. Everything here is both green and red.
Yeah. That's the same thing. That's the same thing I wanted to say, because the two red areas can cover this green area. So which means we are just considering the whole stuff to be the area shaded.
Yeah.
Yes.
And so in this case, we would guess. Our guess is that the red area.
Yeah, is equal to
is about. Yeah, it's about 30 times 3. So about 90.
Yeah, it's 90.
But again, in order to actually figure this out for real, we would need to use calculus. For now, since we don't know any calculus yet, or you seem to know some calculus, but many people maybe don't know any calculus yet. For now, we're just going to use guessing. Okay, the point is to get the ideas. Okay. But yeah, you're right here. You would need to use what's called integral calculus in order to actually calculate this.
Okay. Hello, I still have it. Yeah.
Sure. Mm-hmm.
Yeah. What if you have like considering 2 vehicles?
Mm-hmm.
Yeah. Another vehicle starts at origin and move towards the 3. And another vehicle starts at 30 and moves straight towards 3. What can we say about the errors? What can we say about the error?
Okay, so yeah, it's a good question. I think maybe let me not address that right now. But yeah, I mean, basically, if one car is going on the whole faster than another car, then the car with the higher speed graph is going to have more area under it than the car with the lower speed graph. And so whichever car accumulates more area under it is the car that's going to be ahead, like if they're racing.
Yeah, because the reason I'm asking is that, for instance, if you have, I just want to like put it in a real life logic. If you have an armed robber went to the bank to rob the bank, for instance, and this armed robber robs the bank and leave by 5 minutes late. And before then, those security at the bank, they knew a boy after 5 minutes and decided to chase the armed robber. So it will be like, at what point at what speed will those security drive to catch the armed robber that robbed the bank about 5 minutes late or 15 minutes late, something like that?
Right. So you can ask a version of this question without any calculus if everybody's going at a constant speed, right? So we can talk about that. If it's a constant speed, then this doesn't require any calculus. But if they need to speed up, then, you know, basically, yeah, it's kind of a tough question, but they're going to have to, in order to catch, you know, the robber gets a little bit of extra time. That whole time, the bank people are just going, or the security is just going at 0 because they haven't started yet. So
Yeah.
the robber gets a head start. Let's say this is the robber, and then the bank starts off at 0. So in order to accumulate enough area, they're going to have to go up much faster in order to catch them. So
Okay.
yeah, this is a question that you can ask with some real functions. Maybe we'll do something like this when we do integral calculus.
Okay.
Okay, great. So let me, you know, move on. So let me talk just a little bit about, you know, what are these applications of calculus? So I've shown you 2 problems, the odometer problem and the speedometer problem. Can you get distance from speed, and can you get speed from distance? And both of them, constant case, not so hard to do. We just have this formula, distance equals speed times time. But when they're but when things are changing and moving, then this is not so straightforward. And you need to calculate the slopes of these tangent lines, or you need to calculate the areas under these curves, and these are not easy things to do. Okay, and this is what you need calculus in order to be able to do. So if that was all that calculus could do, then maybe calculus wouldn't be so important and it wouldn't be so widely studied. But it turns out that these 2 basic problems about area under a curve and tangent line, slope of a tangent line, can be interpreted in lots of settings to have lots of applications. So over the next few slides, I just want to run through some applications of calculus in different fields. So the basic applications are in physics. So calculus was invented, you know, by Isaac Newton and Gottfried Leibniz. And at the time it was invented, the main reason for calculus was to do physics, okay? Back this day, every mathematician was a physicist also. Every physicist was a mathematician. It was the same thing in the 1600s. And so what are the basic applications of calculus? So we've already seen one here. We're relating position and velocity and acceleration. So this is maybe the most fundamental application of calculus. It also relates work and force and energy together. If you want to do electromagnetism, if you want to calculate the fundamental laws of electromagnetism, how changing, you know, what is electromagnetism, right? The point is, when an electric field changes, that creates a magnetic field. Or if a magnetic field changes, if you move a magnet, that creates an electric field. It creates electricity. So already you hear these key words, moving, changing. This means that it has to do with calculus. And so if you want to formulate the laws of electromagnetism, like how does movement of electricity create a magnetic field, or how does movement of electrons how does movement of a magnetic field create an electric field? The way that you phrase these laws is in terms of calculus. If you want to do electrical engineering, relate, you know, you have circuits with capacitors and you want to relate voltage and currents in these circuits, it turns out that the laws that govern this are all in terms of calculus. And then I'll just say much, much more. Basically, all of modern physics, anything involving quantum mechanics, anything involving relativity, all of this stuff is phrased in terms of calculus. Okay. So calculus is more or less used in, you know, anything involving physics where your system changes. Anything beyond just like traveling at a constant speed or applying a constant force. Anything more advanced than that is really going to be done in terms of calculus. Okay? So calculus has lots and lots of applications in physics and engineering. Probability and statistics. Lots of applications with calculus. So maybe the most important one is for analyzing what are called continuous probability distributions. So maybe you've seen a picture at some point called the normal distribution or the bell curve. Kind of looks like this. It's supposed to, you know, symbolize kind of where, if you take samples from a large group, where do they lie? Most of them lie here around the mean. These are kind of your samples around the mean, and then there's maybe fewer of them that lie out here, outside at the tails. And if you want to actually like do mathematics with this, like try to understand, you know, what percentage of, like if this is 0, if you know some calculus, if you know some statistics, you can talk about the standard deviation of your data, and you can talk about how much stuff is going to be within one standard deviation. of your mean, and you want to understand how much is under that graph, it turns out that the way to do this is calculus. And more generally, anytime you have these kinds of probability distributions, the way to analyze them and figure out what the probability is that something will happen within some certain range, turns out that calculus is what you want to have in order to be able to do that. Okay, so calculus helps you analyze these continuous probability distributions. If you know a little more probability, it relates what's called a probability density function to a cumulative distribution function. We probably won't talk about that so much, but we can talk about that. We can, if you know those words, then that'll make some sense. And then also, actually, this goes back to what Miata was talking about with data analysis. So let's imagine that you have a bunch of data. You have some, independent variable. And here you have a dependent variable. And so let's say I have a bunch of data points like this, and I want to know whether I think these two variables are correlated, whether I think one affects the other. Well, it looks like here that kind of the larger the independent variable gets, the larger the dependent variable gets. But of course, I've got a lot of messy data. It's not an exact linear relation. So what people do when they have a lot of data like this is they try to draw what's called a best fit line. So a best fit line is something like this. It's a line that best approximates the data. And in order to figure out how to draw a best fit line given a bunch of data, turns out that uses calculus. Okay. So calculus is used a lot in advanced probability and statistics. So one thing for trying to understand these probability distributions, and another thing for trying to understand best fit lines based on data. Okay. So what's another application? So it gets applied in business, economics, and finance. So the second major application of calculus that we're going to do this semester is what's called optimization. So for instance, you have various inputs that you have to your business, and you want to maximize your profit or minimize your cost. This is something that calculus can help you do. If you study some economics, there's concepts called marginal cost and marginal valuation and marginal profit, and trying to understand how that relates to total cost and total valuation and total profit. This is a question for calculus. Understanding how changing an input to an economic model affects the outputs. So maybe you want to understand how interest rates are going to affect the employment rate in the country, or how they're going to affect inflation of the currency. So you maybe have some economic model, and then you want to say, okay, well, if we raise our interest rates a little bit, what's that going to do to the unemployment rate? Or if we raise our interest rates, what's that going to do to inflation in the country? And so when you set up a model and you try to understand how changing some inputs is going to affect various outputs, turns out that calculus is a very useful tool for doing that. Okay. And then this is maybe, less relevant, but analyzing the price of a financial instrument based on its underlying parameters. So, you can buy, government bonds, and you can buy stocks, but there's all of these other more exotic things. There's call options and put options and futures and forwards, and there's all of these strange financial instruments that are based on other financial instruments. The word that's used is sometimes called derivatives, but they're not the same thing as a derivative in calculus. And if you want to try to understand what is the appropriate price of some sort of exotic financial instrument that depends on some other stocks or commodities or something like that, then calculus can help you do that. Okay, so these are just some of the applications of calculus in business and economics and finance. Let me do another one. So we can also talk about applications of calculus in biology and ecology. So it turns out that calculus is great for understanding population dynamics in ecology. So this could be populations of people, but it could also be populations of animals or of plant life in a given area, or even of bacteria in a certain area. How does a colony of bacteria grow and how does it die? Understanding these rates of change, again, this same idea of motion and change, that means that calculus is usually good for studying that. Understanding predator-prey systems. So if you have an animal predator and then an animal that's the prey, well, they can sometimes live in this kind of harmony, right? If there's too many predators and not enough prey, then the predators will die because they're going to starve, and that means the prey will flourish. But then, as more predators die and more prey flourishes, then all of a sudden there is enough for the predators to eat. So then the predators start eating the prey, and the predators maybe flourish, and the prey population goes down. And you can have these cycles of lots of predator and lots of prey. This could be, particularly important for understanding, mosquito concentration in a certain area, where you introduce some predators for the mosquitoes, some frogs or something like that. So understanding these predator and prey systems, again, things changing over time, this is something that is good for calculus. In particular, this is governed by what's called a differential equation. Probably won't get to talk too much about, but this is based on calculus. Understanding infectious disease. So trying to model COVID-19 when it came out, it seems like, is it going to really increase without end? Or at some point, does the population develop some immunity? What happens as you try to chart the course of an infectious disease, whether that's COVID-19 or Ebola or any other kind of infectious contagious disease that you have? This is something that calculus can help you model. And then this is actually a word I just learned. So pharmacokinetics, which is the study of drug concentration in the body over time. So if you take a medicine, you have a lot of it in your body. How long does it stay in your body? How quickly is it excreted from your body? And, does it happen quickly? Does it happen slowly? Does it take a long time? Understanding that is also a question that calculus can be used to help you with. Okay, so calculus has applications in biology and ecology as well. And then maybe the last thing would be just very basic geometry. So almost everybody here is a math teacher. So there's certain formulas from geometry that you really need calculus to do. So if I asked you, what is the area of a circle? Can somebody tell me the area of a circle in terms of the radius? So what's the circle of the, yes, sorry. Yes, Armstrong?
Yeah, it's pi r squared.
Exactly. So it's pi r squared here, where r is equal to the radius. So this is a formula that we've probably all seen, but how do we really know that it's true? And the answer is, to really know that this is true, you really have to use calculus. Okay? So there's not really a way to prove this without using calculus. Okay, and so there's similar things like, what's the volume of a cone? This turns out to be 1/3 pi r squared times h, where your cone looks like this. You have some cone here where h is the height of your cone and r is the radius of the circle underneath. So it turns out that the volume of a cone is 1/3 pi r squared h. What's the volume of a sphere? This turns out to be 4/3 pi r cubed. So if you have a sphere that looks like this, and it has a radius r, sorry, it's red, has a radius r over here. Volume of a sphere is 4/3 pi r cubed. And just more in general, how are circumference and area and volume all related? These are all questions that, require calculus. You need calculus to derive these formulas. Okay, so to get any of these formulas just requires calculus, okay? Because when you're trying to measure the shape of curved things, you just can't do that with your basic area formulas, right? The area of a rectangle is base times height. And from that, last year when we talked about some geometry and trigonometry, we showed how you could get the area, or this is, I guess, 2 years ago, we showed how you could get the area of a triangle or a parallelogram or a trapezoid, various shapes. You could do various reasoning in order to figure out the areas. I think last year we even did a regular polygon with n sides. But once you have curves, then none of that works anymore. So if you're trying to do a circle or a cone or a sphere, once you have curves, basically you have to use calculus in order to get anything to work. Okay, so calculus. So basically what I just want to get through is that calculus has, lots and lots of applications. It can be used in physics, geometry, finance, biology, engineering, probability, everywhere calculus gets used. Okay. So that's maybe something about the applications of calculus. So now, what do we need to know in order to do calculus? Well, if we want to understand calculus, the first thing that you need to understand is functions. Okay, so the most fundamental concept in calculus is that of a function. Okay, so we'll spend a whole class talking about functions, but fundamentally, what is a function? A function is a recipe that accepts an input. That input is usually going to be a real number when we're talking about calculus. And then it gives you an output, which is also a real number in the context of calculus. And that output has to be well defined. So you can't have randomness if you have a function. Okay, so the same input has to give you the same output. So x squared is a function. It's saying take an input, what's the output? You're going to square it. Okay, if the input is has some randomness, like you have a random number generator or something, that's not really a function because the output's not well defined. You need to make sure that the same input is always going to give you the same output, right? So if I say if my input is like a number from 1 to 7, and then my output is, the weather somewhere on Earth on that day of the week. So 1, and then my output is the weather somewhere on Earth, the temperature somewhere on Earth on Monday, and 2, then the temperature somewhere on Earth on Tuesday, so on. These things are not functions because it depends on where on Earth I'm talking about. There isn't one well-defined output. So a function needs to be something that takes an input and gives you one well-defined output. So we're going to spend quite a bit of time at the beginning of the term reviewing functions, and we're also going to talk about the similar concept of relations. So I know this is in the curriculum, and several people wanted reviews on functions and relations for this year, so we're going to talk about functions and relations before we get into calculus. And for us, the most important functions are going to be what are called the polynomial functions, the rational functions, the trigonometric functions, the exponential functions, and the logarithmic functions. So we're going to go over all of that before we start on calculus. So function is the most fundamental concept we need to know. And then what else do we need to know in order to do calculus? Well, maybe the next most important concept is called limits. Okay, so limits, basically everything in calculus has to do with limits. And to actually define what a limit is not so easy. It's pretty hard to do a limit. So this term, we're not going to do rigorous limits. I don't know if anybody has seen rigorous limits. It involves epsilons and deltas, and it's something that, maybe we can do at some point, but probably not this term. So we're going to take a more intuitive approach to what a limit is. But the idea of a limit is to ask how a function behaves near, but not at a given input point. So for instance, if I have a function that looks like this, let's say that this here is, x equals 3, and here I have y equals 3, and I just draw my straight line. It looks like y equals x, but I put a little hole in the graph, and I keep going, and then maybe at the value 3, maybe this takes on the value 5. So I could call this, y equals f of x, some function, and I could define f of x in the following way. So f of x, okay, is going to be, it's just going to be x whenever x is not equal to 3, but it's going to be 4 when x is equal to 3. Okay. 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 All right. So this is my function, and this is the graph, right? I draw it as just y equals x everywhere, except at x equals 3, it's not going to be 3. It's going to be 4 instead. Okay. So what I'm going to say here is that the limit as x approaches 3 of f of x, again, this is just a quick overview. We'll spend a whole time talking about limits. But what we say here is that the limit as x approaches 3 of f of x is that,
Yeah,
well, yes, Tony?
hello.
Oh, yeah, yes, Enoch?
Yeah. If you have the function value to be like two different stuff, like if the function is x at s is not equal to 3,
Yeah.
and if the function is at 4 and s is equal to 3.
Mhm.
So can we also describe this one as a one-sided limit?
Yeah, but it's actually, this is a two-sided limit. This is a full limit. We don't need to
Okay.
describe it as a one-sided limit. What
Okay,
I
so
think maybe you're getting at is this function is not continuous.
okay, so which means, yeah, to know that it's not continuous, you have to set to know if the limit at x or the limit at 4, if you evaluate, it will give you the value where to know if all two equals.
Exactly. Yeah. So that tells you
Okay.
that this is not continuous. But for our
Yeah, sure.
purposes here, the limit here is 3. And what we mean by this, so this is the notation. You say lim, and then you write x going to what value. And what that means is if our x values are getting close to 3, what are the y values here getting close to? Well, as long as we go along the graph, as our x values get close to 3, the y values are also getting close to 3. Okay? And at 3, it jumps to 5. Oh, sorry, this should be 5, not 4. Sorry. This should be 5. Okay. So at 3, it jumps up to 5, but a limit doesn't care. The limit just wants to know what's going on as you get close to a given value. Okay, so in this case, the limit of f of x as x gets close to 3 is 3. So the way we should read this is that as x gets close to 3, f of x gets close to 3. Okay. This is what we mean by limit. And again, we'll study it in much more detail later on, but we mean what's going on near a value. And this is a little bit unintuitive for lots of people. And this is one of the reasons why people find calculus hard, because understanding what it means to say near something is not the easiest concept. So it's a concept that just requires practice. And then eventually you get used to it and you get used to dealing with it. Okay. So let me just give a couple more examples and then we'll finish because we're running out of time. So one example would be, so what is the limit as x approaches 1 of x squared minus 1 over x minus 1? Since for time, I'm just going to go through this quickly. We'll spend more time on it when we do this. Or,
Yeah.
okay, enough. Do you want to do it?
Yeah, the answer will actually be just 2.
Yep. Okay.
Yeah,
Yes,
sure.
that's right. So how do we do that? Well, the point is x squared minus 1, we can write it as x minus 1 times x plus 1, right? Divided by x minus 1. And then we see that we get a cancellation here, right? We have the x minus 1 here cancels out with the x minus 1. And so this is going to be the same thing as the limit as x goes to 1 of x plus 1. And now let me just draw a picture. So what is this function? Well, it looks like we've crossed it out. And so this function is exactly just the same thing as x plus 1. But in fact, it's not exactly the same thing as x plus 1. So I can draw y equals x plus 1. That looks like this. And this is y equals x plus 1. But actually what's going on with this function is at the value 1, what happens if I plug in 1 over here? I get 0 over 0, right? If I plug in 1, I get, 1 squared minus 1 divided by 1 minus 1. And that's 0 over 0, and that's undefined. Okay? And so what that means is that this function is actually like x plus 1, but it's got a little hole here at 1. Okay? But the moral of the story, oh, sorry, and this is 2 over here. So at x equals 1, it's got a little bit of a hole there. But the limit doesn't care. The point is the limit doesn't care about the hole. As far as the limit's concerned, as you go toward 1, there's no hole because we're only looking at points that are near 1. And what this cancellation tells us, so this is going to be 2, like Enoch said. Because for x plus 1, what happens to x plus 1 as x gets close to 1? Well, as x gets close to 1, x plus 1 gets close to 2. Okay, so this looks like y equals x plus 1. And again, as x is getting closer and closer to 1, we go along this graph. That means that the y value or the function is getting closer and closer to 2. Okay, so in this case, we say that the limit is 2. Again, if you've never seen limits before, this is probably very fast. Don't worry, we're going to do it in much more detail later on. I'm just giving an overview. Let me just talk about the second type of limit, which would be an infinite limit. So what's the limit as x goes to infinity of y equals 1 over x? Well, the graph of y equals 1 over x looks something like this. And so
This
what do we
one,
mean?
this one.
Yes.
Hello.
Yes, enough.
Yeah. Or what if in real life, if you have the limit at x approaches infinity, some value 1 over x, in real life approximation, why I decide to say that the answer the answer of the function goes to 0, something like that.
Exactly.
Would that be correct?
Yeah, that'd be correct, right? So the point is, what is this asking? This is saying as x gets really big, what happens to 1 over x? That's what this is saying. As x gets really big, what happens to 1 over x? And from this graph, we see, so maybe you've seen this under the word asymptote, right? So you've maybe seen that this function has an asymptote at y equals 0, okay? And so the answer here is that as x gets big, 1 over x gets very small and goes towards 0. Okay, so as x gets very big, 1 over x gets very small and goes towards 0. So what we would write here is that the limit as x goes to infinity of 1 over x is equal to 0. So again, I don't expect you to be able to do a problem like this after seeing these two examples because I've done them fast and I haven't really laid the groundwork. But I want to just give you a feeling for what happens with limits and why calculus reasoning is maybe different from reasoning that you've done in other classes, right? So in calculus, you're worried about what's going on near a point, and you have to be able to talk rigorously about the concept of about the concept of nearby. So yeah, sorry, one second, Enoch. So here we have to know what's going on near 1. Here we have to know what this function is near as you go out towards infinity. And so part of what we're going to do this semester is get some practice talking about these concepts. Okay, yes, Enoch?
Yeah, like I was saying, yeah, in another analysis, because we see number on the number line, they are uncountable on the number line.
Yeah.
So yeah, in some suggestion, if you are giving the limit value as the value given approaches some value like positive or negative infinity, and we know that going to positive infinity is a kind of a huge number. So yeah, so for instance, if this 1 over x, if you are firstly taking the value beginning at 1, if you take s value to be 1, and this will going to be it will be 1. And secondly, moving to the next level, if you are taking s value to be 2, the value is going to be 0.5.
Right.
And next, if you are taking it to be 3, it will be 1 divided by 3, which will be 0.33, something like that. So if you are taking it if you are taking s value to be 4, it will be 1 divided by 4, which will be 0.25. So these value as you are taking those values in ascending orders on a lower line, this value will be approaching 0. So as this number goes infinitely to some value, so it was just approximated that it is actually 0.
Yep, exactly. So this is a great explanation. And you can think of, right, you take x getting bigger and bigger. So if x is 10, you get 1 over 10 is 0.1. If x is 100, 1 over 100 is 0.01. If x is 1,000, 1 over 1,000 is 0.001. And as you're going bigger and bigger, you're getting closer and closer to 0. So the way we encapsulate that in the language of calculus is that we say that the limit as x goes to infinity of 1 over x is equal to 0. That doesn't mean there's actually any x you can plug in that gives you 0. I can't, infinity is not a number. I can't say 1 over infinity is 0. That's not well defined. But I can say that the limit as x goes to infinity of 1 over x is 0. Say that in the limit, you're getting closer and closer to 0. Okay, you're getting arbitrarily close. Okay, so basically, what are we going to start with? I showed you the syllabus before, but the idea is we're going to start talking about functions and relations and limits, and then we're going to move on to the differential calculus this semester. And I know that, please don't be intimidated if you've never seen any of this before. We're going to try to start, from the very basics and build up to being able to talk about calculus. Okay, and of course, starting again next week, we'll get everybody their data before class starts. All right, so thank you for your attention. I'm looking forward to journeying through calculus together. It's going to be something new, and I hope that you're going to enjoy it. So,
Yeah,
and one more reminder: if you have not written your
hello.
name yet, 1 second. If you've not written your name yet in the chat, please do so, because I save the chat and then I have a record of your attendance. Otherwise, I'm going to forget that you're here, and you may not be able to get your data. So most people wrote their name, but I just want you to double check that you put your name in the chat somewhere. Yes, questions?
Hello.
Yes,
Yeah, you were saying something about the function and relation. Are we doing it today? I wanted to ask a question on it.
Sure.
Are we continuing with function and relation today? I wanted to ask.
No, we're done. We're done. We're finishing. We finish at 6.
Okay.
Yeah. So class will go from 4 to 6.
Oh, okay.
Yeah. All right. Any other questions? Okay, great. Well, thank you all for coming. Again, hopefully next week we'll have the data distributed faster, and we will and so that way everybody can join closer to on time, so we can go for the full 2 hours. Okay, and so I'll send the attendance list to Sange today, and she should be able to reimburse you for your data soon. Okay, so everybody have a nice weekend. Yes.
Hello.
Yep.
Yeah, I really want to know if will today's video be posted in the chat room for some
Yes,
viewing?
I will post the video later today.
Oh, okay.
I'll post in the chat room, and I also send the notes, and then I also post the video on YouTube.
Oh, okay. Okay, nice.
Yeah. Okay, you're welcome. And the videos will always be on YouTube, so you can always watch them on the channel.
Okay.
Great.
But for some of us, we don't actually have the link to the channel, so I beg your
I'm going to
indulgence.
send the link. In fact, I don't even post the video in the chat room. I just post, because the video is too big, so I post the link in the chat room.
Okay.
Yeah. And the link, by the way, is in the syllabus, which I posted to the chat room. There's a link inside that.
What?
I posted the syllabus to the chat room just before class. And if you open the syllabus, there's a link to the YouTube channel.
Okay.
Yeah. Okay. Other questions? Okay. So if there's no more questions, then thank you very much for attending.
Yeah.
Sorry.
This is
Yes.
Enoch again.
Yep.
Yeah. When I was joining it live, I saw something like the meeting schedule. The time will be meeting like today the 13th, next month, and the continuous stuff. So I want to see that in the chat room also for it to be like guidance.
It's all in the syllabus. So I sent the syllabus to the chat room. Yeah. So this is the schedule. But this is all in the syllabus, which I sent to the chat room about 2 o'clock today.
Okay.
Yeah. So this is the schedule for the semester. But I sent this. I mean, I'll send the syllabus again, but I sent it. Let me see. When did I send the syllabus? I sent it today at about 2:30.
Okay. So
to the chat room.
and
And I'll also post this on the website.
Okay, but there are some things I want to understand in detail, but I know now time are going against us, so I will test you in your personal inbox on WhatsApp.
Okay, sounds good.
Okay.
All right. Great. Okay, so have a great weekend, everybody, and I'm looking forward to seeing you next week.
Okay. Thank you, sir.
Thanks, you're welcome. Bye.